For centuries, humanity has gazed at the cosmos with wonder, seeking to unravel the mysteries of its creation. Today, we stand at the precipice of a new understanding, a paradigm shift in our comprehension of the universe's origins. This is the theory of universal motion, a compelling alternative to the prevailing Big Bang model. The Big Bang theory, while dominant, has its limitations. It struggles to fully explain certain observed phenomena, such as the universe's remarkable homogeneity and the existence of the cosmic microwave background. The theory of universal motion offers a fresh perspective, proposing that the universe did not erupt from a singularity, but instead emerged from a state of absolute stillness. Imagine a universe devoid of motion, an infinite expanse at absolute 0 Kelvin, where energy and matter lay dormant. This is the starting point of our journey. A stark contrast to the fiery chaos often associated with the universe's birth. This theory suggests that the universe began as a vast, cold void governed by flat Euclidean gravitational fields, a concept we will delve into further. It posits that the universe's evolution is driven not by an initial explosion but by the fundamental nature of motion itself. The theory of universal motion presents a radical departure from our conventional understanding of the early universe. Forget the unimaginable heat and density of the Big Bang singularity. Instead, envision an expanse of absolute 0 Kelvin, a state of perfect stillness where even the fabric of space-time lies dormant. This initial state is not a void in the traditional sense. It is filled with a sea of potential energy embodied in the very structure of space-time itself. This potential energy is expressed through flat Euclidean gravitational fields. These fields, unlike the warped fields we observe around massive objects today, are uniform and unchanging, stretching out infinitely in all directions. Imagine a perfectly flat sheet of rubber representing the fabric of space-time. In this initial state, there are no dips or curves, no hills or valleys. This uniformity is crucial because it represents a state of perfect equilibrium, a state of absolute stability. However, this stability, while seemingly eternal, contains the seeds of its own undoing. Within this vast cold expanse, a subtle interplay of quantum fluctuations begins to stir, disturbing the perfect equilibrium of the gravitational fields. The universe, in its state of absolute stillness, possessed an inherent instability. Within the seemingly unchanging gravitational fields, quantum fluctuations, an intrinsic property of the universe, acted as subtle ripples, disturbing the perfect equilibrium. Imagine a single grain of sand dropped onto our perfectly flat rubber sheet. The sheet, representing space-time, would warp slightly around the grain. Similarly, these quantum fluctuations acted as minute perturbations in the flat gravitational fields. This seemingly insignificant event had profound consequences. The destabilization of even a single gravitational field triggered a cascade effect. This disturbance propagated outward, disrupting the balance of neighboring fields, creating a domino effect that spread throughout the universe. This cascade marked the very first movement in the universe, the birth of motion from absolute stillness. It was a moment of profound significance, the transition from static potential to dynamic energy. Section 4. Condensates, seeds of structure in a sea of energy. The destabilization of the gravitational fields unleashed a torrent of energy throughout the universe. This energy, initially diffuse and chaotic, began to coalesce into localized regions of higher density, forming what we call condensates. Imagine steam cooling and condensing into droplets of water. Similarly, energy, driven by the interplay of gravitational forces and quantum fluctuations, clumped together, forming pockets of concentrated energy within the vast expanse. These condensates, though still incredibly energetic, were cooler than the surrounding environment. This temperature difference is crucial because it allowed for the emission of energy in the form of electromagnetic radiation, specifically microwaves. These microwaves, emitted billions of years ago, permeate the universe to this day, forming what we observe as the cosmic microwave background, or CMB. The CMB, therefore, is not a remnant of an explosive Big Bang, but rather an echo of the universe's transition from stillness to motion. Section 5. The cosmic microwave background, an echo of creation. The cosmic microwave background, or CMB, is often cited as the most compelling evidence for the Big Bang theory. However, the theory of universal motion offers a different interpretation, one that aligns seamlessly with the concept of condensate formation. In the Big Bang model, the CMB is explained as the afterglow of the initial explosion, gradually cooling over billions of years. The theory of universal motion presents a more nuanced explanation. The CMB is not a remnant of a single event, but rather a continuous echo of the universe's transition from stillness to motion. As condensates formed, they released energy in the form of microwaves. This process happened gradually, over vast stretches of space and time. The CMB, therefore, is not a snapshot of a single moment, but a composite image, a tapestry woven from the emissions of countless condensates forming throughout the early universe. The uniformity of the CMB, which poses a problem for the Big Bang theory, is elegantly explained by the theory of universal motion. The initial state of absolute stillness and the uniform distribution of gravitational fields naturally lead to a homogeneous distribution of condensates, resulting in a remarkably uniform CMB. Section 6. Vacuum energy, the unseen hand sculpting the cosmos. The formation of condensates was just the beginning. The universe, now teeming with pockets of concentrated energy, was ripe for the emergence of larger, more complex structures. This is where vacuum energy, a concept often shrouded in mystery, plays a crucial role. Vacuum energy, often associated with the cosmological constant, is a form of energy that exists even in empty space. It is an inherent property of space-time itself, always present, always influencing the evolution of the universe. In the context of universal motion, vacuum energy acted as a catalyst, amplifying the gravitational influence of the condensates. Imagine placing weights on our rubber sheet, representing the condensates. Vacuum energy acts like an invisible hand, further stretching the sheet around these weights, enhancing their gravitational pull. This enhanced gravity drew in surrounding energy and matter, causing the condensates to grow larger and denser. This process, driven by the interplay of gravity and vacuum energy, marked the first steps towards the formation of the cosmic structures we observe today. Section 7. Galaxies and stars, from swirling chaos to cosmic order. The universe, now populated by massive, energy-rich condensates, entered a period of intense activity and transformation. The seeds of galaxies and stars, sown in the stillness of the early universe, began to sprout and flourish. These condensates, under the relentless pull of gravity amplified by vacuum energy, began to collapse inward. This collapse was not a uniform implosion, but rather a chaotic swirl, a cosmic ballet of matter and energy. As these massive structures contracted, they spun faster and faster, their rotation driven by the conservation of angular momentum. Imagine a figure skater pulling their arms inward during a spin, increasing their rotational speed. Similarly, the collapsing condensates spun with increasing velocity, shaping themselves into the swirling disks of protogalaxies. Within these swirling galaxies, smaller pockets of gas and dust, drawn together by gravity, continued to collapse, igniting under their own weight to form the brilliant stars that illuminate the cosmos. The universe, once a cold, still expanse, was now ablaze with light and motion.